One of the main concerns I see about using Python for backtesting or algo trading in general is its speed. It famously has the GIL, it's an interpreted language, and performance wasn't really one of the main design goals of the language when it was first created. Python does, however, have almost all of the major data science libraries. There's a vast user base for it, and it's incredibly easy to learn. So in this video, I'm going to show my process for optimizing Python code bases, and I'm going to do that by taking the example backtest from backtesting.py and optimizing the underlying library so that it runs twice as fast as the initial benchmark. So in order to get started here, I've created a couple of scripts to firstly establish how fast the library is right now, and secondly to figure out where the bottlenecks actually are so that we can go ahead and speed them up. To benchmark the library performance right now, I've added the simple strategy from the README I mentioned earlier, just a moving average crossover. We run that 10 separate times and then average the results to get the mean, median, mode, any other statistics that we'd like. I'm particularly interested in optimizing the backtest time. I'm not going to concern myself with the time to import libraries or plotting time or anything else except the time taken to run the actual backtest. As we can see from the terminal, it's about 22 seconds per execution per backtest, so that's the figure we'll keep in mind here as we're optimizing. In order to find the bottlenecks, I've created this profiling script. We're using cprofile, which is a part of the Python standard library, so you don't have to install anything. And all we need to do is do cprofile.run, then the function which we're looking to profile. So it will break down that function and any other functions that get called as a result of calling that function itself. And it will save that to whatever file name you put here. So I just put profile X. And then once you've got this profile file saved down, you can examine that with the inbuilt standard library, but I prefer to use a visualization tool. So I'm using SnakeViz here to give us this nice icicle graph. And so what we can see straight away is that computing the stats for the backtest is actually taking up the most time of any of these sub-processes below the running of the actual backtest. So this is the process that runs the backtest, or the function call rather, and we can see that computing the stats is taking nearly half of the time, almost as much time as the actual backtest itself. And given that computing statistics like the Sharpe ratio or the equity curve or things of that nature are generally very numerical, that we're not dealing with complex Python objects, that marks it out as an excellent place to start this optimization process. Don't worry too much about the specific timings that it's saying. The profiler itself adds a lot of overhead, so these times aren't particularly accurate, but the relative time between them normally is. So if it says something's taking up 90% of the processing time, it probably is, but the exact reported time taken is normally not very accurate. Now that we've chosen the bottleneck that we're looking to optimize, it's time to start thinking about what performance technology to use to remedy this. Now, my first thought was Numba. You may have seen this before on the channel or elsewhere. What Numba allows us to do is for a subset of Python and NumPy code, we can just slap a JIT decorator on a function and immediately get a 10x to 100x improvement. It's really useful for any kind of numerical calculations. However, for this project, I decided against it for two main reasons. The first is that this is a library, backtesting.py. It's designed to be distributed to lots of different people, and adding Numba creates a runtime dependency. So every user will have to go and download Numba. And I've seen it before where you download one library and it depends on one version of Numba, and then another one depends on another version of Numba, and it's a nightmare when you try and get everything to work. It does also add some small runtime latency, as it has to compile the first time the user runs the program, and so all of this runtime logic that's going on is, in my experience, a bit of a minefield for bugs and other issues that can occur when distributing to other people. And as a developer, I've also found the debugging experience to not be amazingly pleasant. You don't get the nicest of errors and stack traces and help finding what's wrong with your code. And I've spent many an hour struggling with cryptic error messages that I just can't understand. For small projects that you're not distributing when you've got less than 100 lines of code, I think Numba is great for small targeted sections like that, but I don't want to use it in this project. I also thought about Cython, and what Cython allows you to do is to incrementally add type hints or low-level CPython function calls into your code to optimize specific areas. Libraries like Pandas and NumPy both use this. However, I'm not using it because it brings with it a whole host of memory safety issues, which I'm quite scared of. And so I ended up going with Rust, which is obviously designed from a memory safety point of view. It's also extremely fast. And the integration between Rust and Python has gotten really good, to the point where you basically just write your Rust function, you write your Python function, and you call the Rust function from Python just like it's any other function. A few other libraries like Nautilus Trader have also taken this approach of having a Rust core, which is very optimized, and then using Python on top of that. It also has the advantage of being compiled by the developer rather than the user. So although anyone working on this library will need to know a bit of Rust, and they'll need to be able to compile Rust code to have the Rust toolchain installed, the actual user of the library, it will be seamless. They won't need anything else installed, any other extra dependencies. If we take a look back at the Icicle chart of truth here, we can identify some sub-functions within compute stats that we can progressively rewrite using Rust, or otherwise tackle if there's an easier optimization. Since we've been talking about Rust though, I thought this function looked like it was a good candidate. So it's called compute drawdown duration peaks, so something to do with calculating drawdowns. And you can see on the left hand side, it's taking about 12% of the total runtime of the backtest just for this one statistical function. Now, given that it's just calculating a drawdown, very numerical, I'm not expecting to have to deal with any Python nuances. So, in my view, a good target to rewrite with our chosen performance technology, which is Rust for this case. If we take a look at the existing implementation, so this is the original version, it's about, 13 lines of code, and is largely just manipulating different series and data frames. Now, I'm no expert in Rust, but due to the way I've set this up, I don't particularly need to be. For one, we've got a full reference implementation here of the exact algorithm for how we want to calculate the drawdown or calculate this function. It's already working step by step. And we also have comprehensive unit and integration tests, about 1,200 lines of them, that come with the backtesting.py library that do things like check that all of these statistics are actually valid for a particular known backtest. And that way, any logical issues that we manage to insert into the Rust refactor will be found quite quickly. Equally, we have the guarantees of the Rust compiler itself, which helps protect us from any memory safety issues, typing issues, generally just a lot of runtime issues that we could encounter. Those are going to be caught during compilation, and the compiler will help us find them. And so with a little AI assistance, I was able to rewrite not only this function, or to implement it rather, but also the functions for calculating the Sharpe ratio, volatility, a few other different statistics. So I'll check out this commit here. And you can see what this function essentially turns into is converting the input to a NumPy array, as Rust can do zero copy reads, so we're not copying all the information to take it into Rust, very important. We're making sure it's of the right data type, and then we just call this rust.compute drawdown duration as if it's a Python function essentially. It's pulling this underscore rust from here, from dot underscore import underscore rust, and it's just using these shared objects here, which are just compiled Rust code, and the source of which we can find in here. It's about 500 lines, so it's considerably more verbose than the Python implementation, where we were using pandas to do a lot of the aggregations and such for us. But if we look below, we can see that we cut the runtime down to about 18 milliseconds. So we took about 4 milliseconds off per backtest, and that takes us about a third of the way to our goal. In this case, if this was the only function or part of this project that we wanted to optimize, I think Rust would be a bit over-engineered for it. But in the future, if we wanted to pursue more and more performance enhancements and move more and more of the code base into Rust, I think it would pay off as opposed to using Numba. Now what I found here is that as I implemented more and more of these statistics, we were getting diminishing returns. As you can see, it's only really this function that takes up lots of the space, at least when it comes to just talking about numerical functions and algorithms, which would be directly sped up by Rust. And all these other slices just get progressively smaller and smaller and smaller. And so for our goal of achieving a 2x speed up, it's not necessarily worth rewriting all of these different statistical functions to get a 0.5% increase. So I started to look for other categories of performance increases that could be achieved without doing any sort of Rust rewrite by just being cleverer with algorithms or data structures. And one of those is staring us in the face right now. So you can see this set item here, which is actually the largest hog of time in this compute stats function. It's taking up the most time out of any of them, even more than the one that we just spent ages writing 500 lines of Rust code for. I was a little bit scared of it initially because it has this dunder set item, and I was wondering what exactly that is. But after a bit of poking and prodding, I identified that it was within the compute stats function. We had this building of a pandas series. So the return object is a pandas series, which gives you a printout of the statistics essentially. And each item has a string label and then some value. So it might be the start date, the end date, it can be anything, it's just a D type of object. It can even be a full data frame, like in the example of trades, or it can be an object in the instance of the strategy instance that backtesting.py returns. And what was happening is that this series was being built up one item at a time. So we were doing s.lock, label equals key, s.lock, label equals key. And that is what this set item is referring to here. And all I had to do to fix that is to simply add all of the separate items to tuples, put those in a big list, and then right at the end, we turn that into a pandas series. Now the reason that works is because, especially if you're adding like a really large item onto a pandas series, it might have to reallocate the underlying NumPy array or whatever data structure it's using to hold that data. It might not fit in there anymore, so it has to reallocate, maybe copy some data around. Whereas if we just build it all at once, it knows the final size of the series and can allocate it appropriately, and it only does the setup once. This fix actually had quite a surprising impact on the timing. So if I run my timing script again, give it a second to compile the Rust and whatever it needs to do, check out the right version, we can see that it's now down to about 13 to 14 milliseconds. So this one algorithmic improvement or improvement to the data structures that we're using, simply by understanding the data structures better, we achieved about as much of an increase as we did with 500 lines of Rust. If we go ahead and generate a new profile now, so if I do uv run chad profiling, and then I run snickviz again, we can see that compute stats is now no longer the number one in terms of how much time it takes. And we see this next function is now actually taking the longest to compute. So let's now look in here. We've already had a good go at fixing compute stats. Let's look in here now. Now, when I looked at this initially, there were a few things that struck me. The first one is these util.py open, low, and high. Between them, they're about 5-6% each. That's about 18 to 20% of the runtime, about 18%. And it's the majority of this process orders function, maybe half of it, or maybe slightly more, is spent by picking the low, the high, and the open. And when I investigated to find out what this actually meant, I had a look in the code, and broadly speaking, what was happening is that within the process orders function, so this is just some function, it goes through and it makes sure all of our buy orders are processed, etc., etc. It was pulling the open, the high, and the low data from this custom data class with a space, not a data class, a data class, and then pulling either the open, the high, the low, and then just taking the final value. So just getting the final value here for the open, the high, and the low is taking about 15% of the total time to run the backtest. Now, obviously, something isn't quite right here, so I looked into the actual structure of how the data class is organized. So this is the data class, as we can see. And when we try and get the open, the high, the low, the close, any of these values, it uses this getArray function, which we can see over here. And what it does is it tries to get something from a cache, and if it's not in the cache, then it will return the open, the high, the low, whatever series it happens to be, by taking the full time series, so all of the open data, and then slicing it up until the current length. This eliminates look-ahead bias within the actual backtester itself. It means that you're only going to get data up until the actual current bar. But when I investigated, this cache was getting cleared all the time. So in reality, what happened is this cache wasn't really getting used, and it was doing the slicing a lot. And we only actually need the last value. So pulling this whole slice is just not actually needed for what we're wanting, which we only need the last value. So I just added this function to the data class called current value, and you just it's very similar to getArray. You just pass it a key, which is a string. It will similarly grab the value from self.arrays using the key, but we only want that one particular value. And indexing into a NumPy array is way, way quicker than trying to slice one, especially as that array gets larger and larger and larger. And so just doing that, we got about a 12% improvement in speed, just from optimizing how we were getting the most recent value of open, high, and low. If we go back to the icicle chart of truth here, after we'd optimized these three, I decided to go take a look at this equity calculation. And again, this can look a little bit confusing, but broadly speaking, what's happening is on every single bar of the backtest, the framework is attempting to calculate the equity. And if we go look at my solution here, we can see that, for example, grabbing the size or the profit and loss or the profit and loss percentage, we were using these generators to go through every single trade which was currently active, walking through each of them, and then calculating the profit and loss for each individual trade, and then summing them all together. And even with the amount of trades that this particular backtest was doing, which is not an awful lot, that was still enough to be one of the biggest bottlenecks in the system. And so all I did to fix this really, from a conceptual point of view, is that rather than calculating the equity at each bar by walking through each individual trade, just keep a track of our open position total. So how much of a particular stock are we owning or are we short? In backtesting.py, we can only own one asset. And as long as we don't make any trades, all we need to do is get the current price and then multiply that price by the amount that we hold. It's just one simple multiplication. We don't need to go through every trade object, iterate over them several different times and sum everything together. We don't need to do that. We can eliminate all that iteration by just caching the amount of a particular asset that we hold at a given time, and provided we don't make any changes, any buys or sells, we just cache that value and save it for the next bar. And with that out the way, with that optimization done, we can find that actually manage to reach our goal, and in fact exceed it, as the median time is now under 10 milliseconds for one backtest with this particular strategy. So I've shown a few examples of optimization techniques that I like. There's rewriting the whole thing in a different language, which is verbose, but it does work. There's being aware of how the data structures work, like we had with the series, so building the series all at once, rather than building it step by step. Just being aware of how a pandas series is constructed and how it has to reallocate every time if you keep adding large objects to it. That's going to save you time. And then finally, the last two were all about caching. So the first one, we got lots of cache misses, and so we added in a little helper function that just got the information that we need, indexing into an array rather than slicing one. And in the final improvement, we added a cache so that we didn't have to continually iterate over new items and instead could just pull from the cache and do a simple float multiplication.